Hello everyone. Today we will be discussing the research paper titled The Power of Choice for k-Colorability of Random Graphs by Varsha, Dani, Diksha, Gupta and Thomas P. A. Hayes. We start with a small puzzle. Suppose you're faced with impending doom. Which of the three would you choose? A stone, the wand, or the cloak? When this power of choice is applied to a random graph, we end up with something called an Archaeopteryx process. The Archaeopteryx process was proposed by Archaeopteryx, hence the name, in 2001. It builds upon the Edis-Renier random graph, which consists of an empty graph initially. At each step, an edge is generated uniformly at random from a complete graph with replacement and inserted into the graph. To this, Archaeopteryx proposed, instead of a single edge, suppose we generate our candidate edges chosen uniformly at random with replacement and then inserting one based on a rule. For example, if we consider the rule where two edges are generated uniformly at random and then choose the edge with minimum sum of degrees of endpoints, then we get the following result. But why do we care about this? Existing works look at Archaeopteryx process for the following problems: the delaying of the giant component, accelerating the giant component, and delaying small subgraphs. In this work, we consider a set of n vertices and a set of k colors. As discussed earlier, candidate edges are generated uniformly at random from the set of edges in a complete graph with replacement. An edge is picked from the candidates based on a rule and inserted into the graph denoted by G. Then our goal is to design strategies for inserting edges into G for different values of k greater than equal to 2 so as to shift the k-colorability threshold. The k-colorability conjecture was obtained by Archaeopteryx and Knorr in 2005, wherein suppose you have k number of colors and d is the average degree of the graph, then for d less than 2 times k minus 1 ln k minus 1, the resulting graph is almost surely k-colorable. On the other hand, if the average degree is greater than 2k minus 1 ln k, then G is almost surely not k-colorable. Hereby, what we mean is almost surely with probability 1 minus little of 1 when n tends to infinity and d and k are constants. With this in mind, we propose our main approach, which is based on divide and strategize. To begin with, we have a set of n vertices and k colors. Before inserting the edges, we partition the sets V and K each into two disjoint sets, as can be seen here. Then we generate our candidate edges uniformly at random with replacement at each step, and then insert one based on some strategy. Then depending on the endpoints of the edge and the partition, two types of candidate edges arise. The first being crossing edges, which are the edges with endpoints in different partitions, as the name suggests. Note that these edges never violate the k-coloring property, since the set of colors in the two partitions are disjoint. The other type of edges that you would end up with are called non-crossing edges, which are generated when both endpoints are in the same partition. These edges need to be inserted with care since endpoints may have the same colors, thereby leading to the loss of k-colorability property. Hence, we prefer inserting crossing edges as much as possible. This gives rise to the following strategy called prefer crossing, wherein You select the first crossing edge generated from the candidates, if there is any. Otherwise, you select the first edge which was generated. But then the question is, why should this delay the k-colorability threshold? Recall that crossing edges have endpoints in different partitions which have disjoint set of colors assigned to them, so they never violate the coloring property, and hence insertion of such edges is favorable. This reduces the problem to maintaining the colorability with respect to non-crossing edges, further reducing to maintaining the colorability property within just each partition. In other words, we are required to maintain the K1 colorability on side 1 and K2 colorability on side 2. Moreover, we are forced to insert non-crossing edges only when each of the candidate edge is a non-crossing edge. This reduces the probability of inserting a non-crossing edge, thereby reducing the expected number of edges we are forced to insert into a partition when using prefer crossing. Another thing to note here is that the non-crossing edges are inserted uniformly at random with respect to the corresponding side. Hence, we can apply the K1 and K2 colorability threshold to side 1 and side 2 respectively, and then take minimum over the two subgraphs with respect to the expected number of edges inserted into each partition, thus delaying the non-K colorability for the obtained graph G, which results in the following theorem. Using the prefer crossing strategy and the K coloring threshold conjecture, we can delay the non-K colorability as follows. For even K greater than equal to 10 and odd K greater than equal to 13, this can be achieved using just two choices. Next, for even K greater than equal to 6 and odd K greater than equal to 9, three choices would suffice. And finally, for K equal to 7, four choices should suffice. Note that this result was obtained using theorem 1 we had discussed earlier. We propose further improvements to this result by using other existing lower bounds on the K colorability threshold conjecture and modified partitioning strategy, which we will go over next. Specifically, for K equal to 11, we assign 5 colors to partition 1 and 6 colors to partition 2, whereas the number of nodes in each partition remains the same. Then we insert edges using the following strategy. Biased prefer crossing for K equal to 11, wherein we generate two candidate edges chosen uniformly at random from the complete set. Then we select a crossing edge if there is any. If both the edges are non-crossing on one side, then select the first one. Finally, if the two non-crossing edges belong to different sides, then select the one on side 1 with probability 0.3, else select the one on side 2. Combining this result with the newer theorems for the K colorability threshold, we get that only two choices will suffice for even K equal to 11. Similarly, for K equal to 9, we assign 3 colors to partition 1 and 6 colors to partition 2. And as before, the number of nodes in each partition remains the same. That is, we divide them equally between the two partitions. Then we insert edges using a similar strategy, which is the biased prefer crossing for K equal to 9 wherein we generate two candidate edges chosen uniformly at random from the set of complete graph edges. Then we select a crossing edge if any of the candidates is 1. Else, if both edges are non-crossing on one side, then you select the first one. And finally, if the two non-crossing edges belong to different sides of the graph, then we select the one on side 1 with probability 0.2, else we select the one on side 2. Note that this is influenced by the fact that we want to reduce the number of edges inserted on the side that has lesser number of colors assigned to it. This results in the following theorem for k greater than or equal to 6 as there exists some edge insertion strategy that delays the non-k colorability for k greater than or equal to 6 by using two choices asymptotically almost surely. That is, with probability 1 minus little o of 1. Next, we move on to the case where k is less than 6. In this case, the challenge is that at least one partition will be assigned two colors, in which case the k-colorability threshold conjecture fails. So we can't use the lower bounds from theorem 1 as discussed earlier. But this does not mean we cannot do anything. In order to use a divide and strategize approach, we first discuss the two colorability of a graph. To this end, suppose we have two colors, say red and blue, and we have a set of vertices denoted by V. We know that any graph that does not contain any odd cycles is two colorable. This implies that any graph that does not contain any cycles is also two colorable. Existing work on the emergence of the giant component for an Archaeopteryx process shows that just before the giant component emerges, the graph hence obtained, denoted by G, consists of multiple components, each of which is a tree with constant probability. Finally, a tree is two colorable since it does not contain any cycles. Thus, just before the emergence of the giant component, the graph hence obtained using the Archaeopteryx process is two colorable with constant probability. This reduces our goal for two colorability to delay the emergence of the giant component, giving rise to the following strategy. For k equal to 4 and 5, as before, we assign two colors to side 1 and remaining colors to side 2. And as before, the number of nodes in each partition remains the same, that is, equal number of nodes in either of the two partitions. Then we insert edges using the following strategy. Avoid cycles for k equal to 2, wherein we generate candidate edges uniformly at random. Then we select the edge chosen by the delayed giant algorithm unless it would form a cycle, in which case we select the other edge. This strategy ensures that 6 choices suffice to delay the non-two colorability asymptotic almost surely. Finally, for k equal to 3, we cannot even maintain two disjoint set of colors. So we follow the following partitioning strategy. The main idea is that each side has a default color, say red for side 1 and blue on side 2. Most of the nodes on each side normally receive this default color. We denote this default color by star and call this coloring a Y star coloring. And think of coloring all nodes with two colors, star and Y, where for non-crossing edges, both points of the edge, that is the endpoints, must get different colors as is standard in a two coloring. But for crossing edges, we allow both endpoints to be stars. This reduces the goal to avoiding inserting YY crossing edges at the same time maintaining two colorability in the graph. This is achieved using the following strategy called prefer crossing but check. In short, PCBC. So you choose 6 edges generated independently and uniformly at random from the set of complete graph edges. Let E be the edge chosen by the prefer crossing heuristic described earlier. Select E if G union this edge E is Y star colorable. Else you select the first edge other than E. This finally gives our main result, which is that there exists an explicit edge selection strategy for our choices Archaeopteryx process that almost surely, that is asymptotically almost surely, can delay the non-k colorability for k greater than or equal to 2 using anywhere between 2 to 6 choices as specifically described throughout this presentation. For details, please refer to our paper, and thank you for listening to this presentation.